The POLARIS Framework and POLARIS activity-based model are being developed as part of an open-source software project. Developers can customize POLARIS on different technical levels. The most fundamental components are the POLARIS core libraries. These libraries provide tools for handling memory allocation, discrete event simulation, inter-process communication, and other low-level but essential features used across nearly all transportation system models. Problem-specific libraries implementing agents, objects, and functions to support specific simulation concepts are implemented on top of these core libraries. The problem-specific libraries are intended to be extensible and used across multiple projects. Accompanying these problem-specific libraries are other utilities that are not built on top of the POLARIS core, but that are generally useful and necessary for model development. These include network editing tools, data conversion tools, scenario management, and more. Many of the libraries and utilities rely on mature open-source projects, such as SQLite, Spatialite, Boost, Python, and OpenGL, to handle details such as graphics processing, database management, and GIS functionality. Finally, full applications can be built from the general libraries to address highly specific issues. An example is the integrated ABM simulator. This is the simulator that has been introduced earlier in this presentation. The entire POLARIS software framework, including the core libraries, object libraries, and simulation applications, is freely available for download, development, and usage from the GitHub repository shown here. The software is licensed under a permissive BSD open source license, which allows modification and commercialization provided proper attribution is given to Argon. The code itself is being developed in C++ and is cross-platform compatible. The code repository includes scripts that utilize the CMake universal build system to allow compiling the code using the Visual Studio Integrated Development Environment on Windows and the free GCC compiler on Linux. A few other less-known platforms are supported as well. The POLARIS framework provides a highly customizable visualization library that allows any simulation object to be easily drawn in the POLARIS user interface. The library provides all the necessary functionality to draw to multiple two-dimensional plotting layers, as well as the three-dimensional full visualization environment. The 2D plotting allows for XY plots and bar plots, which are dynamically updated while the simulation is in progress. The 3D environment allows any object to be drawn at its current location throughout the simulation. Most importantly, the visualization environment provides powerful identification and interaction capabilities for any object displayed in the 3D environment. This means that the current state of any object can be identified, and functions can be used to interact and modify the states of any selected object. The POLARIS network editor is being developed within the Transim Studio open source project. Both POLARIS and Transim's version 5 share the same internal network representation, which is contained in a spatial SQLite 3 database file. In addition to the Transim's network components, POLARIS has a number of additional objects, such as variable message signs, radio towers, variable speed signs, and other objects representing ITS roadside infrastructure. The network allows for consistent network editing and integrated error checking. When nodes are moved, the ends of attached links follow them. When links are moved, attached activity locations follow the new shape of the link. This happens in both visual space and in the underlying database. Using a database, the editor can internally enforce referential integrity on the database level, protecting the database structure from major corruption even if a user application crashes. Another advantage is the convenient packaging of a consistent network within a single file. This makes it easy to identify network versions and to distribute consistent versioned networks to others. The use of spatial extensions provides a comprehensive set of geospatial processing functions. In addition, the network database is supported out of the box by the powerful Quantum GIS software, an open-source equivalent to Esri's ArcMap software. The POLARIS framework also contains a scenario management utility for running detailed parametric studies. Due to uncertainty and the statistical nature of traffic analysis, any input parameter may have a range of valid values. For example, when simulating weather impacts on congestion patterns, it may be necessary to run simulations for a variety of different weather conditions, such as snow, fog, or rain. The Scenario Manager provides the capability of specifying the most important simulation input parameters as value ranges, rather than as fixed values. It will then create many feasible combinations of these parameters sampled out of the allowable ranges, and submit the resulting scenarios to a high-performance computing cluster, such as the one available at TRAC. Each job is a full simulation of the transportation system, resulting in a slightly different result for each job. The Scenario Manager will then provide the tools to evaluate the different outcomes, giving the user a better understanding of the sensitivity of each input parameter. The Results Analyzer is a utility designed to quickly and easily perform data analytics on the databases created by Polaris simulations. The analyzer provides a graphical user interface that allows the user to perform these tasks with minimal knowledge of the SQL query language. Several statistical tools are available in the analyzer, such as averaging, least square fits, and histograms for performing common statistical analysis and aggregation tasks. The outputs can then be used to generate graphs and charts for visual analysis and inclusion in reports. The graphing tools in the Results Analyzer allow the user to visualize data to be used in reports and for the quick comprehension of large amounts of data. The data processing capabilities of the Results Analyzer allow for tabular data to be reshaped and transformed in a variety of ways. This data processing work can be performed through SQL queries or by using a more user-friendly graphical interface. The processed data can be visualized in multiple ways using graphical formats such as XY plots, scatter plots, and pie charts. The processing and graphing procedures can be stored in a file and reused across multiple simulation results. The Polaris framework uses file-based SQLite database for storing input data as well as simulation results. This includes specifically the route network, but also the outputs from the different tools. These databases provide a common data interchange format that can be easily extracted and converted to be compatible with other modeling packages. A C++ interface library is used to communicate efficiently between Polaris applications and those databases. The ODB interface does not require any knowledge of SQL syntax, but provides for the persistence of any object as needed. The Spatialite extension for the SQLite database engine allows the developer to easily perform complex spatial operations. The core libraries of Polaris handle much of the low-level functionality required for the development of high-performance agent-based simulations. The core libraries form the foundation for all other Polaris libraries and applications. Some of the key features are a discrete event engine, which enables models to be written from an agent-based perspective. The engine allows the developer to specify agent actions and action timings and automatically handles the scheduling and execution in a multi-threaded manner. The core also provides high-performance memory allocation and memory management, which are optimized for large-scale transportation modeling applications. The structures provided for creating agents are automatically instantiated in a thread-safe fashion, which is important considering the time-dependent nature of transportation simulations and the high degree of interdependence between agents. Finally, the core libraries also provide the means for handling inter-process communication over distributed processor networks, such as a cluster computing environment. For developers, Polaris provides a customized set of inheritable objects and specialized keywords that simplify the task of quickly developing agent classes and code libraries. A simple example is the creation of a Polaris Traveler object and is discussed on the slide in more detail. First, a developer would start with a simple Traveler class written in standard C++ with a number of public member functions and private data members. This class is then split into a set of specialized Polaris objects, the prototype and the implementation. The prototype acts as a general interface to a related family of objects with no specific data members of its own, while the implementation represents a concrete class of the object, in this case a traveler with a floating point data member as shown in the original C++ class. Simulation objects built up from the Polaris core use the prototype implementation pattern described previously. Objects inherit from a common Polaris base component, which gives the developer access to the Polaris core features, such as memory management, threading, execution scheduling, and so on. In general, this design pattern provides all of the advantages of using conventional interfaces, such as encapsulation, abstraction, and increased code resiliency. In addition, this pattern puts a greater emphasis on referring to objects using type names rather than concrete types. This allows the code to become more referential and qualitative by communicating more information to developers, increasing the code's resilience. The design of the prototype extends interfaces by allowing optional and required members, instead of having all members to be required at all times. This allows the prototype to extend to a larger set of underlying classes. These characteristics and style conventions give Polaris objects a unified look and feel, which improves the extensibility and ease of use of the code. This concludes the presentation on the Polaris framework and related tools. Thank you for your interest.